Hello guys, good evening and welcome to this class on integration. Okay, so I'll do a recap of further integration, just a quick one so that you can be revising in your free time. Okay, so further integration is just a build-up of the integration that we did before, that was before binomial expansions. Okay, so further integration is divided into some parts. So basically here we're just looking at advanced methods of integrating certain functions. You see, there were certain functions under the beginning of integration that we couldn't integrate because we were limited with methods that we had learned. So further integration is actually a build-up of integrating certain kinds of functions. So here we are looking at, so the first method of integrating under further integration is using the concept of partial fractions. So using the concept of partial fractions. So the idea here is that you have a function of this kind here. You have this function here, x plus 1. So you want to integrate this function. But you see, it's not easy to integrate this function using the methods we learned in the first part of integration. So that's the more reason why this further integration comes after you've done partial fractions. Now, I challenge you guys to go and revise partial fractions that you did with Mr. Mkua. So you have to revise the topic that you did on partial fractions because further integration using this method depends on partial. Okay, so yeah, we want to integrate this function. So the first thing that you do is that we want to do some partial fraction on this function there, which is x plus 3. Before we integrate, we have to break that function there. So breaking it down, you remember with the partial fraction that you did is writing it in this form, x plus 1. Then from here, the idea is that we want to break this function into these units here. Why do we want to break it into these units here? Because you guys, you remember that we talked about integrating functions of this kind during the first part of integration. And we said that this function here, integrating it, is just writing that a, which is this is a, which if you want, we can even write it in front. Then lean this thing here, that's all. X plus b. That means we have integrated. So we know this, okay? And then not only that, you also remember that if we have this, integrating this with what we did during the first part of integration, we said that, you remember here, you can see here there's no constant here. Okay, there's no constant here. And remember, we are only dealing with the ones with power 1, not bigger than that. We'll look at that later in the sequence of the lesson. So we are only considering this. So this, you can only use this concept here if the power here is 1. And remember here, there was no constant. If there was a constant here, we would have written a constant down here. So like here, there's a constant. So the general integral of functions of this form, the z constant will be 1 over this constant here becomes that way. And then now we write lean, then 2x plus 3. So we are using these concepts here, and that's the more reason why we're interested in, whenever we have a function of this kind, we want to break it down into these two things that we know here so that we can integrate. So the whole reason of doing some partial fraction is because this is what we know. So we want to, any function given in that form, we want to break it down into what we know. Because after we've broken it down into this, we can now integrate using the idea that we know. So this means that now we're going to have, now you have to make sure you check, you find your A. I found my A, you do your partial fraction. I found my A using partial fraction. I found it as 5/3. And I found my B as -2/3. So you have to check that if you do your partial fraction. Then now, after you found A and B, or after you've done your partial fraction, so this just means that this function here, which is x plus 3 over x minus 2, x plus 1 dx can now be broken down into 5/3, that was A, x minus 2, B was 2/3, as I wrote it, 2/3. And then we have x plus 1. So this function here can be broken down into this. So instead of integrating this function, we can integrate this. Integrate individually. Can integrate because this function here is the same as breaking it down like that. So integrating this function is easily done using this way. So then we know how to integrate functions of this kind. 5/3 is just a number. Then you want to integrate 1/x minus 2. This one here. 5/3 is just a number, so I've written it outside. So we want to integrate this using this idea here. Using this idea. So here we have a 1. So it will just be 1. Lean what is down. So here it will just be 1. Lean this, which is now just like that. But it has to be in the modulus because logarithms don't accept negative numbers. That's why we always put it in the modulus. So this is minus. We also write 2/3 there. Then we set in x plus 1 plus c. These are indefinite integrals. They have no limits of integration. That's why we put c. So we put c for all indefinite integrals, those that have no limits of integration. So that's how we do it here. So this is the idea of partial fraction. So the idea of partial fraction functions is these, we actually call them rational functions. So we are integrating rational functions. These are rational functions. These are rational functions. So the rational functions, those are the functions that we are doing partial fraction on them before we can integrate. So that's about partial fraction. Okay, that's about partial fraction way of integrating. So you have to make sure that you write it in that way. That's the idea. Even if you have a function, for example, this is the one I'm going to leave as a task for you as you go through this, you can do some practice. So if I'm integrating maybe this function here from 4 up to 5, then we have x squared here minus 3x plus 10 over x squared minus x minus 6. Then you want to integrate this. Now you see, it looks very complicated, but it's not as complicated as it looks. It's quite very easy to integrate because we are using partial fraction. So the whole idea is we need to do partial fraction like we did here. We need to do partial fraction. Now you can see that here, this was already factorized. This was already factorized. So we just went straight to express it in that form. Now here you can see that The down part is not factorized. So you have to do factorization of this so that it comes in this form before you could break it down as A over plus B over plus whatever. So you need to practice this, guys. Go through this and check it out and get the answer. Okay, so that's about partial fraction way of integrating. Nothing complicated here, guys. So that's partial fraction way of integrating. The other method or the other part under this, apart from rational function. So this is the first part under further integration. The second part is integrating functions of the form 1 over x squared plus s squared. So we are integrating functions of that form here. Now, integrating functions of that form uses the concept of tan. Remember, if you remember inverses of trigonometric functions, for example, tan inverse, okay, the derivative of this, guys, using implicit method is 1 over 1 plus x squared. Using implicit method of differentiation is actually 1 over 1 plus x squared. What do I mean? It's that way of where you write you have y is equal to tan inverse of x. Okay, and then you introduce tan on both sides. This side you introduce tan, the other side you introduce tan, so that you have tan y here, because when you multiply throughout by tan, this side you multiply by tan. Remember I said any function you multiply by its inverse, you need to try to get a 1. So now here you have x, so you're not getting 1, so you have x here. Then we differentiate on both sides, yeah, using implicity, and then that's how we get a derivative. The derivative of tan inverse as that. So this form here uses the concept of the concepts we use in differentiating inverse of functions, inverse of trigonometric functions. So what does it say? So this says actually that under this you have, if you have a function that looks like this, then using, this is A. This A is standing for any number. Then you just use this criteria that this A will be, this is the squared, but it's a square root that should be here. So tan inverse x over A plus C. That's the integral. The other format under this is you have a part that looks like 1 over 1 plus b squared x squared dx. And then you have, of course, 1 over b, which is just the square root of this part. Then you have tan inverse of bx plus c. Now you can see that if b is here together with x squared, inside it will be bx here. If a is standing alone and x squared is standing alone, it will be x over a here. So any function that is in this form, we can express it either in this form or in this form, because these are the two forms we know on how to integrate functions of such form. So what would be the example? The example, guys, would be if I have maybe this function here, x squared plus 25, we're integrating with respect to x. Now you see that this is which form? This is the first form, the A. This is this form here. We have just swapped. Here we have just decided to write x squared here, s squared there. Nothing, but it's the same. Okay. So, you know, this side, guys, this one is 25 plus x squared dx. If I want to write it in this form here so that you don't get lost. Now you can see here that this is 25, which is a squared. So a is the square root of 25. If you look at this here, this is a squared, but here we use the square root of a squared. So here a squared is 25. The square root of 25 is 5. So we have 1 over 5. Then tan inverse of what? x over a. So it's x over what is a? A is 5 plus c. That's the integral. That's the integral. So this criteria of integrating just uses or integrates functions that are in that form there. So one thing about integration, guys, is that sometimes there are a lot of criteria and methods you are using. So when you look at a function, you should quickly be able to know what criteria or what method am I using. Am I doing the partial fraction way, or am I using some time? And yeah, so you need to figure out that, guys. Okay, so that's about that. Maybe one would wonder, you can see here a squared is standing alone. Here b squared is here. Maybe one would ask now that what if you have now something of the form a squared plus b squared x squared? Yeah, like there's a squared and b squared at the same time. Well, the whole idea is you just express this function in either of that form or in this form. If it's in this form, you're making sure that here there's no b squared. If it's in the second form, you're making sure that here there's no a squared. Demonstrate that. Maybe I would write it as an example where, let's say we have, I would write maybe 1 over 9 plus 16 x squared. Okay. So look, we are using two expressions, 1 over a squared plus x squared. The other one is, this is the first expression. The second expression we are using is 1 over 1 plus b squared x squared dx. So now look, this expression requires that x squared is standing alone, doesn't have a coefficient here apart from 1. So if I want to go this route, then it means that I don't need that 16 there. So I can factor it out. So I'll have 1 over, so I'm factoring out 16, right? So I'll write 16 that I've factored out. Now factoring out is the same as dividing through. So since I've factored out 16, it's like I'm dividing through. 9 over 16 plus x squared, because I factored out 16 dx. Now, when I do that, you actually see that in this case, my a squared is 9 over 16, meaning my a is 3 over 4, the square root of that and the square root of that. That's my a. So meaning if I'm integrating using this criteria, which is this one here, it will be 1 over a tan inverse of x over a. Now, in this case here, so we have 1 over 16 times 1 over a, you can see here. What is our a? Our a in this case is 3 over 4. So times 1 over 3 over 4. And then we have tan inverse of x over a. What is a? A is 3 over 4 plus c. And then the next thing is you have to simplify this. Yeah, you have to simplify this and you get the answer. So that's a task I simplify. So you have to simplify that. But we can also choose to do it in this way, using this idea here. How? If we are using this idea, then we require that the first number is standing alone. Like we don't need 9, we need a 1 there. So that would mean we are factoring out 9. So we have 1 over 9, and then we have 1 there. Factoring out, like I said, is the same as dividing. So here we have 1. So plus, that's dividing by 9. So we have 16 over 9. Then we have x squared here. And then after we do that, if we express it in that way, meaning we are integrating in this, using this idea here. Where we have 1 over b, which means in our case, b squared is what? 16 over 9. Meaning b is what? Meaning b is 4/9. That's the square root, guys. Meaning B is 4/9. Right? Yeah, meaning if we're integrating using this format, 1/B, so it would be, remember there's already a number outside there, so I would write it first. Then I say times 1/B, what's B? B is 4/9. Then we have tan inverse. Look at the format, Bx. What is our B? B is 4/9x plus C. Simplify that as well. Simplifying, I just mean multiplying this. That's what I mean. Simplifying, I just mean multiplying that. Yeah, so that's about integrating using this part. So the whole idea is that any function that is in that form, you want to write it either in this form, it's either in the form of A, which means you're using that method, or it's in the method of, it's in the form of B, meaning you're using that concept there. Yeah. So that's about integrating functions of this kind of expressions. All right, guys. And then the third under this further integration is integrating functions that are of this form. What do I mean by this form? Like what we have something down whose derivative is what is on top. So your function down as a derivative which is on top. So we use this way. So what's the idea? So the idea is if I'm integrating a function of this form, the only thing you do is you just make sure that you check if they are really derivatives of each other. If they are, then that k is just a scalar, guys. It's just a number. If you want, we can even write it outside because that's just a scale. So the moment you identify that the functions are derivatives of each other and dividing in this way, then you use this criteria here that the integral would just be k ln this thing which is down here, the function. Please normalize writing moduluses here for every function. The reason is because we are trying to avoid negative numbers and logarithms. They don't exist. So plus C. So this is a general way of integrating any function that looks like that. They are derivatives of each other. Yeah. So what do I mean by that? So what I mean is, look, we have this function here, x squared plus 2 dx. Now you guys, you know that our f of x is x squared plus 2. Now check the derivative of that is what? Is 2x, which is what we have on top. So these two guys here, the numerator and the denominator are just derivatives of each other. So then I can use this criteria, this idea here, that the answer is just going to be, there's no k in our case. There's no any other number here. If this here was the 6x, okay, on top here, if it was 6x, would have written it in the form 3 times 2x, so that this 2x is the derivative we are talking about. And then this 3 number would have been our k. Now, in our case here, in this function, we have no k. K is just 1, it's a constant. So then it just becomes ln the function down, which is what? X squared plus 2 plus c. So that's the integral there. So the whole idea is you just make sure and to check that the functions you are integrating are derivatives of each other. Sometimes integration requires that you guys you become smart. You just look at the function and then you think quickly what method you are going to use. Yeah, it's not like differentiation. Differentiation, you just look at the function. Sometimes, even without thinking, you're able to know, here I'm going to use this method, here I'm going to use this method. differentiating. Integration is sometimes comes out in some in different ways, such that you at the end of the day you learn a lot of methods, and you try this one, it fails, you try the other one, it fails, you try the other one, it fails, which is not good at the end of the day, especially if you're writing an exam, because time is going, and at the end of the day you require to at least answer much of the work. So that's the more reason why you need to know these criteria, these methods very, very well, and practice, because the more you practice, the more you familiarize yourself. Each time you see a function, you're able to relate because you did it somewhere, you practice. So that's the more reason why you need to make sure that you practice, especially integration. So that's about this method, guys. Yeah, that's about this method, guys. Sometimes we could have a function like, like this one here, where we have cos 2x over 1 plus sine 2x dx. Yeah, maybe we are substituting 0 and pi, we're integrating from 0 to pi. Yeah, 0 and pi. So maybe I put pi over 2. Yeah, so maybe you're integrating from, or if I swap them, from negative pi to pi. So one thing, if you look at this function here, if I take the denominator as my f of x, which is 1 plus sine 2x, let's get a derivative of that. What's the derivative? It will be 2 cos 2x, right? The derivative will be cos 2x. The derivative will be 2 cos 2x. That's the derivative, 2 cos 2x. Now, you see that this is here, but the 2 is not there. 2 is missing. So the only way is we are thinking there was a 2 in front here. That canceled with that for it to remain without a 2 here. So that's how we think. And the reason why is so that when we are integrating, we are going to use this criteria here. This criteria here. So meaning if we have a 1 over 2 there, that was supposed to cancel with that 2, because that's the only way the derivative, you can see that the derivative doesn't have a 2 there. So it means we have 1 over 2, then ln 1 plus sine 2x here. Then we're substituting negative pi to pi here. And then the answer becomes, we start off with first of all, put pi there. What we get, ln, if I put pi here, I'll get 360. I'll have 2 pi. Now remember, sine 2 pi is 0. Okay, so I am going to have 1. Then 1 minus 1 over 2. I do the same, I put negative pi. I'm going to have as well 1. So that finally the answer will just be 0 as the final answer when I integrate that. So I've used this criteria here that functions are derivatives of each other. So that's about this method here, guys. Yeah, that's about this method. So we are now number what? Which other, we are now on which method? Number what? So we've done 2, we've done 3. So we are on number 4 criteria under this. So which is, of course, the method of integration by parts. So this integration requires that you have functions that multiplying like this. Yeah, your functions that are multiplying like that. That's what it requires. So your functions that are multiplying like that. Where does this method come from? This method comes from, you remember guys under differentiation. Under differentiation, you remember we had what we call product rule. Now, product rule, we are saying if we have functions of this kind, what was the derivative? If you remember, it was u dv dx plus v du dx. I'm just taking you back to product rule. And now look, you guys, if we, of course, this is what we said, if we are differentiating something of this kind, we use this method. We're even writing it as uv prime plus vu prime. Okay, so now look, guys. So let's do this now. Let's do this. Let's introduce integration on everything. Now, you know, when you integrate, if the derivative of the integral of a derivative, it's like you are going back. What do I mean? You have a derivative here. This is a derivative with respect to x. If I integrate this, let's say I'm integrating, so this is a derivative of u with respect to x, right? The integral of that is u itself. It's going back. Integration is like going back, okay? You differentiate, the moment you introduce integration, it's like going back, okay? So now look here, we have the derivative of uv. We have the derivative of uv that we are using product rule. So when we introduce this integration here, it's like we are going back, so we have uv, and so this is going to be, remember there's integral here, u dv dx. Someone would say, why am I not writing? Since we are going back, why am I not here? I just wrote direct uv. It's because we are just talking about the derivative. Here we have the derivative of uv. So we've gone back to uv. Here we have two things. You have e and dv dx. So when you are going back, you can't just write any, because you have two functions here. So this one here, this one is a derivative. The other one is not a derivative. So I've written it the way it is. Plus, I'll write this one the way it is. Now you've seen what I've done. So I take this, the other side. What am I going to have? I'm going to have uv minus, because it's positive. So when it goes this side, it will be minus. So minus v du dx. You can see. So this will remain like that, and it's positive. So I'll write it here. U dv dx. Now I don't want this dx down there. So what can I do? I can multiply it throughout, right? I can multiply it throughout. I can multiply it throughout, but yeah, I can multiply it throughout if I don't want it, right? Yeah. So now look, that's where this whole thing comes from. That's where this formula for integration by parts comes from. So integration by parts, like we said in class, that you have two functions. So the formula is like this: u dv Then we have uv minus v du dx. Yeah, dx like that. And I said that you have a function maybe of this form here. So integration by parts would mean we are going to let x be u, and then dv, so that exponential function would be dv, right? That would be dv. And then meaning that now, like I said also, that you need to be very careful. Sometimes these functions can be swapped. Let's say they were written like this. Yeah, and then you would say, maybe let me let this to be u. Let me get this to be dv. You have issues to integrate. So in your choosing here, you need to be a little bit careful. U should be a particular function that it's easy to differentiate. And also, as you continue to differentiate certain functions, let's say they should have some possibilities of disappearing. The more you continue differentiating, you should be able to reach at some point where you get a derivative at 0. Like the way we have here, the derivative of this is 1. If I differentiate again, I'll get 0. So you choose this to be u. You choose this to be dv. Yeah. There are certain functions you actually see anyway. They don't disappear. You have a case where both functions, there's no function between them, where if you choose that function to be u and you keep on differentiating it, it's not disappearing. Of course, yes, there are such kind of functions. But from the best point of view, let me just tell you that. So you need to be very careful on choosing which one is your u and which one is your dv. You must choose a particular function which is easy to differentiate, and sometimes it should be able to disappear the more you keep differentiating. dv should just a particular function which is easy to integrate, because remember you have dv here. This is a derivative. dv is a derivative. Okay, dv is a derivative. This is dv dx, remember in the formula from here. That's dv dx. So this is dv dx, which is a derivative. So meaning if to get v, you are integrating. So remember that is dv dx, which is a derivative. To get v, you have to integrate. So you integrate the derivative to get v. So this is dv. To get v, we'll always be integrating dv. Yeah, because we need to have v here in the formula. We need to have v here in the formula. Of course, we have du dx here, which means you'll just be differentiating the u function you choose. So if you choose u to be x, meaning your du dx is going to be 1. And if you choose this to be your dv, it means the integral of that is what? Is itself. The integral of this exponential function is itself. So with that said, it actually means if I'm integrating this function here, I'm going to have, of course, my u is x and dv is this. And using that formula, guys, it means from here you can see that u dx is what? Is 1. And you can see that to get your v, you're integrating dv and you get that. So this is your v. Okay, so it actually means that your u is x, your v is this that we have gotten, minus what's the v? V is that, which is the way it is. Du dx is 1, so we can just have that. So then the final answer is this. The integral of that is itself. So that's the integral of this function here, using integration by parts. Okay, so we actually even use this same method to integrate the line function. First of all, you know that the derivative of ln function is what? The derivative of this ln function is what? It's just this, the derivative of that, which is 1 over itself. Right? Yeah. So we are using the concept that differentiation of something which is in that form. This is ln f of x would be f prime of x over f of x. That's the criteria also under differentiating logarithm function, natural logarithm function. So it will be the derivative of the function over the function itself. Now, what of integration? Because that's differentiation. What of integration? So integration, we also do the same. We are writing it in this form. This ln x here, we write it as ln x times 1 dx. Remember, this will not change anything. It's still ln x. So we are just writing in that form so that we can use integration by parts, where this will be u, and then this will be dv. So that to get du dx, we get what? A derivative of ln x, which is 1 over x. And then to get dv, remember dv is 1. So to get your v, you are integrating the integral of that with respect to x is what? Is x. And then we use the formula, which is this formula here. So u from here, u is ln x. V from here, v is 1 over x. Or v is x, not 1 over x. Minus the formulas, minus the integral of what is v? V is x. What is du dx? The derivative of ln is 1 over x. So you can see this and this will cancel. So you only remain with the integral of 1 here. So you have ln x times x, which is x ln x minus the integral of 1 here is as x. So it's x. So minus x plus c. This is the integral of ln x. Okay, that's the integral of ln x. That's the integral of ln x. Okay, so that's about integration by parts, guys. That's about integration by parts. Integration by parts is integrating functions that are expressed in that form. Then you are using this method here. Yeah. So please make sure that to familiarize yourself with this method, make sure that you do all the questions on exercise 8.4. Please go through. When you get stuck, that's why I'm around. That's why I'm there. Yeah, that's why I'm there. I'm like a coach. My job is to make sure that I help people with challenges. Yeah, and make everyone better. So please, guys, practice those questions under exercise 1.4, 8.4, I mean. So that's about integration by parts. What remains is for you guys that you go through and attempt as many questions as possible so that I can know better where to help you, where to come in and help one another. So that's about integration by parts, which is number what? Number 4, right? Yeah, number 4. And then the 5th one is substitution method. The 5th one is substitution method. Now, substitution method is, what is the idea behind substitution method? The idea behind substitution method is that you've been given a function, but you realize that the function, so let's say you've been given a function in terms of x. So you have to integrate your function with respect to x, where your function is in terms of x. But you realize that it's not easy to integrate that function as it is in terms of x. So you think of the way you can transform it into another form, maybe in terms of u or in terms of whichever letter or whichever variable that you use. Okay, so you transform it in that way, which is easier to integrate. And then after you get the answer, you either take it back to x or to being in terms of x, or you leave it in that form. So you mostly leave it in that form if you are dealing with mostly you have been given limits of integration where you have to find also new limits of integration. Then we've talked too much. Let's see what it's all about. So suppose we are given this function here. We're given this function here. And then you want to integrate. Now you think of it, sometimes it becomes more complicated when you look at it. What method am I going to use to integrate this function? Well, it's not hard. It's not difficult to integrate this function. And that's why this method of substitution method works. Well, that doesn't mean that there's no another method that can work. There's a method that can work, but maybe that method is very complicated and you may have issues trying to get the answer. So that's why the substitution method comes in, and that's why it's there. So how does it go? So look, if you look at a denominator, this is a square root. Okay, this is a square root. So what I'll do is I'll let what is down, I'll call it u squared because it's a square root. If it was a cube root, I would have said u to the power 3. If it was a fourth root, I would have written u to the power 4 here. But it's a square root, so I'll call it u squared is equal to x plus 1. So what is inside there? If it was a cube root, like I said, it would be u to the power 3. It was going to be equal to what is inside, but it's a square root, so that's why I put squared there. Then after that, you realize that if u squared is equal to x plus 1, it means that u is equal to what? U is the square root of that. Remember, you're just introducing square root on both sides. So if u squared is that, so u is the root of that x plus 1. So then after you do that, now you see that if u squared is equal to x plus 1, what would be x? I'm making x a subject of the formula. So meaning I'm taking 1 this side. So I have x is equal to u squared minus 1. You've seen, right? Yeah. And then from after you make x the subject of the formula, like in this case, look, what if I differentiate x with respect to u? What do I get? I'm just differentiating this, so it will be 2u. And then I make dx a subject of the formula. So what am I going to get? Making dx a subject of the formula, I'm just multiplying these guys. So it will be 2u du. Right? 2u du. That's what I have. So dx is 2u du. So meaning this function now I can write it as 3. What is x, guys? X, I call it u squared. U squared minus 1. Over, what is the square root of that? It's here. It's u. What is dx? It's here. It's 2u du. This u and u can cancel, guys. And then what do I remain with? Look, this is just a number I can multiply with that 2 to get 6 and write it outside. Right? Then I'm just going to have u squared minus 1 here. Yeah. And then now look, what if, so I have a 6 there. What would be the integral of u squared? Just using the power rule of integration, which is u to the power 3 over 3, right? It's just increasing by 1 and you drop the same. Minus integral of 1 will be u. We put c because these are indefinite integrals. So that's the answer. So we have 6 u to the power 3 over 3 minus u plus c. Yeah. But if I want, so now I was just using some u to make integration easy for me. So I have to take it back in terms of x. But what is u? U is the square root of that. So I can go back and substitute. So I have 6. What is u? U is the square root. That. To the power 3 over 3 minus, what is u? U is that. Plus c. That's what I have, guys. You see, I end up with that. Sometimes it's important to simplify. 3 here into there, it's 2. We multiply this 6 by that. You've seen. I've integrated using this substitution method. I've integrated. The other idea under this same method of integration is we are integrating a function of this form. In short, you have a square root, and then you have some number, some perfect number, minus x squared dx. So it's in that form in short. So the moment you identify that it's in this form, a number minus that, we use this substitution here. X will be a, so we use, we call it trig substitution. So we call it trig substitution. So that's a there. So anything that is of this form, where there's minus, we use this idea here. We make substitution of that. A is a square root of a squared, then sine theta. So this is exactly in that form. So then I would say, I let x be, a in this case, this is a squared, a in this case is 2. So 2 sine theta. Then after that, so meaning why there's x here, I'll substitute 2 sine theta. What of why there's dx? So I need to get the derivative of that with respect to theta. And then I'm going to have 2 cos theta. That's a derivative. Then I make dx a separate formula from here, which means I cross multiply here. Just have 2 cos theta d theta. Then after I do that, what do I do next? I can now go back and substitute in my function. So I have the square root of 4 minus, what is x? X is 2 sine theta. So I have 2 sine theta squared because x is squared here. What is dx? Dx is 2 cos theta d theta. Now look, this is what? So I have the integral. This is 4 minus 2 squared is what? Is 4. Sine squared is what? Is sine squared. Then I have 2 cos theta d theta. Now look, this gives me 4 is common on both, right? So I can write it like that. These 2 here, if I want, these 2 here, I can write it in front. There's no problem, it's just a number. So that here I only remain with 2 cos theta d theta. Now look, here now I have things that are under that root there. What's the square root of 4? It's 2, right? So 2 times 2, I'll get 4. The square root of 4 is 2, so I've multiplied with that 2. So that inside here, I only remain with 1 minus sine squared theta cos theta d theta. Now look, this is a trig identity that you know. You have this trig identity here. Cos squared theta plus sine squared theta is equal to 1. What happens if I take sine squared the other side? Our cos squared theta is equal to 1 minus sine squared theta. So guys, this is cos squared. That's cos squared. It's cos squared. So this is cos squared. But what's the square root of cos squared? Because this is in the square root. What's the square root of cos squared? It's cos theta. That's the square root. So then it means this is just 4, and the square root of that is just cos theta, which will multiply with that cos theta to get what? Cos squared theta d theta. Now I want to integrate this now. So how do we go about to integrate that? So now we have this cos squared theta d theta. And remember, I told you that mostly when we're integrating this, we make substitution of 1 over 2, 1 plus cos 2 theta. If it's sine squared here, we make substitution of 1 over 2, 1 minus cos 2 theta. That's what I said. So that's what we are going to do here. So 4 in the integral of 1 over 2. So this is equal to that. So I'm just doing that substitution. 1 plus cos 2 theta. You need to know these things, guys, because mathematics, every concept depends on another concept. So you need to revise everything. So 1 plus cos 2 theta d theta. which is, this is 1 plus cos 2 theta. 1 plus cos 2 theta. So this is 2 here is 1, 2 there is 2. So just have 2, then 1 plus cos 2 theta, then d theta. So this is equal to 2, what's the integral of 1, guys? With respect to theta, it is theta. Plus, what's the integral of cos 2 theta? It is sine 2 theta, and the 2 drops it down. You shouldn't forget that concept. Then plus c. I can expand this, guys. 2 times theta is 2 theta. Plus 2 times this, it will cancel that 2. So you only remain with sine 2 theta plus c. So that's the answer, except that your answer is in terms of theta. I want to write it in terms of x because the function was given in terms of x. I just used this substitution to make my work easier, to integrate the function easier. So I can now write it back. I can now write it back in this form. But remember, sine 2 theta from this expansion here of theta plus theta, in short, the expansion you learned of a plus b, is just the same as 2 cos theta sine theta. This sine 2 theta is the same as that. So this is the same as 2 theta plus 2 cos theta sine theta plus c. So now I want to substitute. I don't want theta, I want the x's. So what do I do? Now remember the relationship we established earlier, that x is equal to 2 sine theta. We said x is equal to 2 sine theta. From here, guys, you can see that sine theta is equal to what? X over 2. You just divide both sides by 2. So sine theta is x over 2. Meaning, if you're using the triangle, guys, to see properly, this is theta. Remember, sine is opposite from SOHCAHTOA. So remember, sine is opposite of hypotenuse. So opposite is x, hypotenuse is 2. From Pythagoras theorem, this side will be what? 4 minus x squared. Yeah, from Pythagoras theorem, that side will be 4 minus x squared. So meaning, sine theta is x over 2. If I want to know what cos theta is what? Adjacent of hypotenuse. So adjacent from here is what? Root 4 minus x squared. What's hypotenuse? Hypotenuse is 2. So that's cos theta. So here I can substitute 2. What is theta from here? So from here, theta will be what? Theta is equal to sine inverse of x over 2. Right? From here, how do you find the angle theta? Is theta a sine inverse x over 2? So this theta will be sine inverse of x over 2 plus 2. What is cos theta? We said is this 4 minus x squared over what? Over 2. What is sine theta? It's x over 2. Then plus c. So your job is simplify this. You cancel some 2 and yeah. So this is the final answer. That means you have integrated. So we integrated in terms of thetas, and then we want to write our function in our original what? In our original form, which is x. So that's how we integrate this thing, guys. The other thing, actually, if you remember very well, I think we had looked at, which is 1 over 9 plus x squared. I just want to emphasize to you that you remember we looked at integrating functions of that form, which is exactly this form. And we said the general formula is 1 over a tan inverse x over a plus c. That's what we said. This is actually in this form. So the reason why it actually becomes that way is because I just want to tell you that from this substitution that we have talked about here for sine, here if we are adding there, we actually use this substitution. X is equal to a tan theta which is this one here, except that in our case, A is what? A will be 3 in our case here. So that's what so this general formula is actually generalized from this here, okay? So the reason why we come up with this criteria is because we are using this substitution here before we conclude and give you something which is like the general formula to use, where you don't have to go this way, because this comes from this substitution we are making here, that x is equal to a tan theta. Like in our case, a is 3. So I would say I let x be 3 tan theta, so that I differentiate this with respect to theta. Remember, the derivative of tan is sec squared. So this is 3 sec squared theta. And then I want what? To have the dx there. So I make dx the sub to the formula, which will be 3 sec squared theta d theta, right? And then I go and substitute now the function. 1 over 9 plus, what is x? X is 3 tan theta. This is squared. So when you square, what do you get here? 3 squared is 9. Tan squared is tan theta squared. Then what is your dx? Dx is 3 sec squared. So this dx here so this dx here is this that we have here. So that's 3 sec squared theta d theta, guys. Then now from here we have the integral of, on top, I can just write this on top, there's no problem. Over, look guys, 9 is common, so I can write that. Sorry, we don't have d theta there. Now look, this is a trig identity again. What is 1 plus tan squared? 1 plus tan squared theta is equal to sec squared theta. Remember that trig identity. So this is the same as sec squared theta, which will cancel with this sec squared theta, which is on top. So this and this, which is sec squared theta, will cancel. So you only remain with 3 over 9. You see? So you only remain with 3 over 9. Then you are integrating with respect to what? To theta. And you come up with what as the answer? 3 and 9 is just a number. You can even take this outside. There's no problem. So this is just the same as I can write 3 over 9 outside, and I'm integrating just 1 with respect to theta, which will just be theta plus c. And then you can see, guys, that 3 here is 1, 3 here is 3, then I have theta plus c. I've integrated, but then I want to write it in terms of x. How do I write it in terms of x? We're going to use this relationship we established here, that x is equal to 3 tan theta. So x is equal to 3 tan theta, right? So this is the same as x over 3 is equal to tan theta along this side, right? So meaning theta is equal to what? Finding theta alone, the tan inverse of what? X over 3. So this is 1 over 3 tan inverse of x over 3 plus c. Right? Now you see, this is just the general formula we are giving you here. So this general formula we give you here is because we are deriving it using this substitution, which you have seen here. We have ended up with the answer. So that's about this substitution here. Okay, that's about this substitution. This is trig substitution, where we are using some trigonometric functions to integrate. We substitute and then we integrate. So that's about this substitution here, guys.